Okay, on to basics part 2. So, this section really talks a lot about what's in the Kline book. And so, that book is a lot more theory-based, and we're going to use it to supplement the Buchanan book that's more practical-based. And so, he talks about a couple of different types of approaches. Strictly confirmatory models, alternative models, and model generation. And so strictly confirmatory models, which is what the Byrne book talks about, is that you have a theorized model and you accept it or you reject the model, and that's it. Done. So you don't ever look at any other things. So here's my theory, here's my test, end of story. I would argue that that is not necessarily what actually happens. And generally people consider alternative models. So I have a couple of different models that I think might be correct, and I compare the differences between them. And so that kind of approach happens when you have different theories that sort of posit different ideas. This is especially true in confirmatory factor analysis, where sometimes people think, oh, it's a 4-factor model. No, it's a 6-factor model. And multi-group models, where you're comparing models to see which one fits best. And so this is where I'm going to be able to focus on which model is the best fit for the data. And then model generating approaches are when you take an original model, it doesn't really work, and so you edit it. So I might modify the order of the variables or where the arrows are going into based on modification indices. And so this is sort of model building versus theory-only approaches. And so this is the part where we're going to get into specification and identification. So we're really working up here talking about. And so you model specifications where I draw out my model and I've determined how I'm going to measure it. And then I have to see if it's identified. We'll get into what does that mean in a second. If the model is identified, I would collect my data and test that model. If model fit is good, then I would go through and sort of test alternative theories and report the results. I don't know what happened to 5 in here, but this is from a book. Okay. Oh, here's 5 over here. If the model fit is not adequate, I would re-specify my model. So I might actually go all the way back up to the top here. But right now we're going to talk about what is this thing up here, and then adequate fit will be in the next section with fit indices. So specification is a term for making the hypothesis and drawing out the picture that you're testing. So we're specifying the model. What do we expect it to look like? Oops, wrong button. Okay. And there are some, not mistakes, but errors that you can make in this stage. And generally it's called the love error or left out variable error. And that's when you forget to measure model of pictures that are important, or you've left out something theoretically that's very important. And there's not much you can do at that point except go back and run the data again. And so this is when someone goes, well, why didn't you consider this? And you're like, oh, just because we didn't, we forgot. And so this is important sort of theory-wise to make sure you understand what you're testing and what variables might be related, and even some variables that you don't think are related, maybe test them. So if somebody says, well, why didn't you include X? You could say, well, we did and it didn't work. Okay, so that's specification. Moving on to identification, sort of a brief pause. You have to understand in identification that SIM is analysis of covariance, or if you could standardize it, correlation. Okay. And that means that I have all of the variables and I've created the covariance between them, the relationship between each variable, measured variable. So we're trying to explain as much as that variance as possible. So for, if I have a 10-item scale, I have every covariance or correlation between those items. So if this one goes up, this one goes up, this one goes up, this one goes down, and by how much. And what we're trying to do with SIM is explain why these 4 go up together and these 6 go up together, and otherwise they're not related. Okay. So we're taking that covariance table, or if covariance is confusing to you, think about it as correlation. So we're taking the correlation table and we're trying to explain why those correlations happen, where they happen. I can also estimate a mean structure. And so mean structure is estimating the correlation table and the means for variables. And that's usually when you want to understand factor means. So an actual number for the circles. And we'll do that when we get to multi-group models where we're looking at means across groups. Generally, this is a covariance only type of estimation, but you can also do mean structures as well. So general rule for sample size, and then getting back to identification. It's called the NQ rule. So N is the number of people in your sample, and Q is the number of estimated parameters. We'll get there in just a second. And so we want our N to Q ratio to be 20 to 1. So if I have 10 predictors, I need 200 people. Or 10 parameters, rather. And that's sort of the perfect world. Or 10 to 1 if you can manage it. So if you have 10 parameters, at least 100 people. Most generally, people don't say go less than 100 on sample size because there's just not enough people to assume that the estimates are going to be reliable. So 100 is kind of the lower cutoff limit, depending, but the bigger the better. Alright, so on identification. So models that are identified have a unique answer. Okay? And to have a unique answer, that means that the matrix is invertible. And without getting into a whole lot of matrix algebra, invertible matrices have independent columns. Okay? And we've talked about this in my other classes some in dealing with multicollinearity or additivity. Okay? So we can't have columns that are perfectly correlated. That is not invertible. Because columns are not unique. Now, when I talk about unique answers, that means that you have one likely answer for all the parameters you're estimating, and not multiple answers. SIM is an iterative process and is not a closed-form solution. Okay, so what I mean by closed-form solution is that if I say x plus y equals 4, you know, there are actually multiples answers for that. And so that's not closed form. Okay? A closed form solution is when there's one and only one answer. Okay? With SIM, what we're actually looking for is one probable answer. And it doesn't mean that it's the right answer, but it means that it's the most likely answer. So we're going to use estimation, which is the math, to find that likely answer. Okay? So we're looking for models that have a unique answer. And if it has lots of possible answers, that model is not identified. So if I say x plus y equals 4, that has lots of answers. They could both be 2, they could be 1 and 3, they could be negative 100 and positive 104. So there are lots and lots of answers. That's bad. And the way we practically deal with identification is we look at the parameters that we're going to estimate, calculate the degrees of freedom based on that. So let's talk about both of those. A free parameter will be estimated from the data. A fixed parameter is set to a specific value. Fixing parameters, is to scale the data to create a standardized solution. Usually they're set to 1, but there will be times that we'll have some model problems where the models won't, you can't get a solution out of them, or you can fix parameters to other things. But generally fixed parameters are set to 1. They'll talk about times when they're not, and those are not estimated because they're fixed. A constrained parameter is a different thing. It's estimated from the data, but in a specific way. So I might be able to set multiple paths or parameters to the same name, so I could call them all cheese, for example. They're going to be estimated, but we're going to force them to be equal. So that's why the word is constrained. It's constrained to be a specific estimate, but I'm still going to estimate it. That's often called an equality constraint, and we'll deal with those when we get into multi-group models, where we're going to force the groups to have the same estimates. So I'm still estimating, but instead of 2, I'm estimating 1 for both groups. Cross-group equality constraints are for multi-group models. It says estimate this path, but make it equal for each group. Some other things that we're not going to really use in this class but exist are proportionality constraints, where I am expecting this path to be 2 times this other path. An inequality constraint, meaning that they actually cannot be equal. And then nonlinear models, so curvilinear models, or quadratic, so x squared, or 1 over x kinds of models. So we can constrain paths to be not straight lines. So let's figure out what's being estimated in these pictures. So here's an example of a very simple CFA. And what's going to happen to make sure this model is identified, we are going to put this little 1 here. So adding that scaling parameter, so that's a fixed parameter, allows us to make sure the model is identified. And we're going to a couple more slides and hopefully that piece will click for you here. If we didn't have this, we would run out of degrees of freedom and we would not be identified, which would be bad. The other thing this does for us by adding this 1 is it scales the parameters. So in a standardized solution, they're all in the same scale. In a non-standardized solution, this one will be 1 because it's fixed, and that will help us estimate the other ones. So what am I estimating in this picture? So each path without the 1, so this one's fixed. So 1, 2, 3, 4 regression coefficients. Okay, so these are B's, the slope, the way that this measured variable is related to this latent variable. Okay, and I think about this in EFA, these are the loadings for EFA. Okay, so 4 of those, 3, 4. Each error term, remember error terms are not shown in the pictures we're going to create, is also going to be estimated. So everything with a single-headed arrow gets an error term. So I've got 6. So 1, 2, 3, 4, 5, 6. This doesn't count because it's a double-headed arrow. Okay. So we've got 6 variances. This path isn't estimated, but the error is. Okay. Each factor is going to have a variance. So variance here and a variance here. That's 2 of them. So each circle gets a variance term. Not error, variance. Different thing. Okay. Then the covariance area, or the correlation here. So 1 there. So we're going to estimate 6, 10, 13 paths. So 1, 2, 3, 4 regressions, 5, 6, 7, 8, 9, 10 for the error variances, 11, 12 for the factor variance, and 13 here for covariance. Okay. Generally what people forget to estimate is these factor variances. So your circles get, or your, sorry, not your circles, your exogenous variables get variances, your endogenous variables get errors. Okay? And we'll do a bunch of these. Now, how do I get degrees of freedom? Degrees of freedom has nothing to do with sample size. No n-1, none of that. It is unrelated to sample size. I could have 8,000 participants in this data set, or 4, and it would still be the same thing. Okay, 4 wouldn't run, but you get the idea. It is unrelated to sample size. Instead, it's about possible number of parameters that you could estimate for this model. Okay. So we're going to do p times p plus 1 divided by 2, where p is the number of squares. So if I go back and look at this model, I've got 6 squares. 1, 2, 3, 4, 5, 6. Okay. So 6 times 7 divided by 2 is 21 possible parameters. So degrees of freedom is possible parameters minus estimated parameters. So I would have 8 degrees of freedom for this model. I had 21 possible, I estimated 13, and then I have 8. Okay. So the hard part really is not this part, the possible parameters, because if you can count squares, you can get that. It's making sure you understand where each estimate is coming in. Now, if you don't totally get this at first, that's okay. What you can do is look at the output for your data and just count the number of things that actually estimated. And those things that are estimated will also be tested for significance. And so that we can figure out how many possible parameters there were, how many actually got estimated. That subtraction is the degrees of freedom. Okay. So what has this all got to do with identification? Well, a just identified model is I'm estimating as many parameters as I have options. So that means degrees of freedom is 0. that is a bad idea. It won't run. It'll give you a whole bunch of mess. You want to always have more possible parameters than you do things that you're estimating. So this is why one good time, like more variables are good for you. Or delete some of the paths. Okay, so just identified models often look perfect because they don't have any other options, right? The degrees of freedom are 0. So this is bad. Over-identified models, this is good for you. So when you have more possible parameters that you could estimate than you actually do estimate, so degrees of freedom is a positive number. So the example I just gave you of the simple CFA is a over-identified model. Okay, so it's a positive number. That's good for you. An under-identified model is when you're trying to estimate more parameters than possible. Degrees of freedom is negative, and these things actually will not run because you don't have the room to calculate the numbers you're looking for. And so you always have to have more parameters than possible. Okay. Empirical under-identification is when two of the variables that you have are so highly correlated that it reduces the number of parameters you can estimate. So if you have two squares and essentially they're the same column, it's going to freak out because even though you should get more degrees of freedom, more parameter options with two squares instead of one, they're so close together that it just assumes that it's one. This is why you always need to check for additivity of your squares. Even if you have an over-identified model, you can have under-identified sections. When we get to fully latent models or full structural models, we'll talk about you have to check the identification for the measurement model, the CFA part, and the structural part. So you can have problems where you think it's identified because literally the number of squares minus estimates works out okay, but one section might not be identified. Okay. All right. So this setting things to 1. So that's called the reference variable, and it's the one that you set to 1. And I use you here lightly because in Lavon it's whichever variable you type first, but you can change that. And the reason that we do this is to help with the degrees of freedom. So it keeps things over-identified. It allows the variables to have a scale, so this is part of scaling, and just generally helps things run smoothly. You don't have to scale this way. You can actually scale in slightly different ways, but we'll get into those more when we're actually typing on the models. So with identification, you have to scale in some form. You can either scale by setting a reference variable to 1 or setting the latent variable variance to 1. Both are fairly popular. I think reference variables are more popular because that's the default. But you have to do some sort of scaling, and that helps with identification and scaling. Okay. As a side note, the variable that you set or scale doesn't actually matter. The only time it might matter, just like conceptually or theoretically, is where the observed variable that you picked doesn't actually relate to a latent variable. Now the model will still be the same, the fit statistics will be the same, and the standardized solution is the same, but sometimes the individual B parameters change. And whichever variable you scale, you don't get an unstandardized estimate. Okay, so you don't get the B slope. You do get a standardized parameter, so you can see if the variable loads like what you expect it to load. But if you want a p-value for that parameter, you can run the model once, change the reference variable, and run it again. Okay. So the whole point of this reference variable or scaling idea is to help with identification. That's the most important thing. Keep it more degrees of freedom than 0. Give the variables a scale so we can standardize them, but it really, really doesn't matter which one you pick. Another side note, this particular chapter that you should be reading talks a lot about second order factors in CFA. We're going to get to that later. But really he's talking about in this section to talk about each section of the model is identified. So sometimes what you'll see is the measurement model has one reference variable and the full structural model part has another reference variable. And that you just sort of have to play with to see what sort of configuration works best for the model you're working on. And that's the general pattern, where there is a reference variable for the the measurement model. The structural part is usually a variance is set to 1. So what do you do if, when you're running one of these models, you get an error that the model's not identified, especially if you have a complicated model? Now, Lavon does its very best to always help you keep things identified by setting reference variables for you. You can turn that off and change how they're referenced, which I don't really recommend unless you know what you're doing. But let's say you have a fairly complicated model with lots of measurement models and several structural components. Start small. So make sure each measurement model runs first, since they have the simpler identification rules. Then slowly add the relationships between them to see where the whole thing breaks down. So we're going to take that measurement model, each little measurement model piece, make sure it runs, then slowly add the relationships between those measurement models or any other variables to see what happens, why it's not working. Alright, so with the Kline chapters, Chapter 2 is a really great review of regression, Chapter 3 is a really great data screening review, and Chapter 4 talks about all the different programs that you could possibly use. So it talks about AMOS, EQS, Literal, and we're going to use R this semester. It's also M+. So there are a bunch of different programs. The great thing about R is that it's free. The bad thing about R is that it's not the easiest one to use. In Chapter 5, he talks about specification, more of the symbols. Chapter 6, he talks a lot about identification. And on page 130, this is the 3rd edition of Kline. It's got a purple cover. I don't think I have an example of it. I don't see it on my wall, but it has some specification rules of thumb that are really great to save. Alright, so with identification, anytime you get a matrix not definite error, and this is true of regular regression too, or let's say you're trying to run Mahalanobis, you have to have what's called a positive definite matrix. Okay? And so this is really getting a little into the math of why we scale and why identification with degrees of freedom and stuff. And anytime you see this error at any point, what it's saying is that the matrix is singular. Okay, singular matrices do not have unique columns. The eigenvalues are negative, so the combination of variance is negative. That's no good. Variance should be positive. The determinant is 0 or negative. The determinant is about being able to invert a matrix where each column has to be unique. Or the correlations are 2.2. And so mathematically that's not true. You can't do that. But you can sometimes get those solutions, and that's not good. Something went wrong. So anytime you see matrix not definite, the most common problem is that the matrix is singular, meaning that the columns are no longer unique. So with a singular matrix, each column has to be unique. So if I have two columns that are perfectly correlated or are linear transforms of each other, you'll get a singular matrix. And so let's say here's a common thing that'll happen. You are trying to work with the subscales of a scale, and you also have a total score. Well, the total score is the addition of the 3 subscale scores. So if you put all of those columns in there together, that total score is no longer unique. It is perfectly correlated with the 3 additions, the addition of the other 3 columns. Another thing that'll happen to people is they'll reverse code columns and leave both columns in there. And those are perfectly correlated because they're just a mathematical transform of each other, meaning if you have a 7 item scale, 8 minus 1 is the 8 minus the column is the way that you can reverse code things kind of easily. Those are going to be perfectly correlated with each other. The way to find this problem is to run a correlation table of all the variables you're using and look for where things are highly correlated. Negative eigenvalues, right, remember the eigenvalues from EFA are combinations of variance, so it's sort of like grouping variance chunks together. And the formula for variance is squared, so it has to be positive. So if you get a negative eigenvalue, something has gone seriously wrong because variance should be positive. A determinant is a product of those eigenvalues, so it can't be negative. And anytime you have a singular determinant, a zero determinant, that means it's a singular matrix. And 1.5 zillion years ago, I had a professor that made us calculate these. It is miserable as all get out. So just take my word for it. Anytime you have determinants that are negative or zero, that's bad for you. That means the matrix is singular. And sometimes things can be out of bounds. And we'll talk about this particular problem a lot. It's called a Haywood case, where the data is estimated to have a negative variance or a correlation over 1. They happen when it's just hard to estimate whatever parameter you're looking at, and so you'll get these wild, crazy estimations. And so if the correlation's over 1 or the variance is negative, you know something's wrong. Generally, this is caused by columns that are too highly related or latent variables that are too highly related. So the individual columns are fine, but the latent structure is too highly correlated. And so that is the end of identification and just sort of a basic understanding of degrees of freedom. So we'll talk more about how do I identify specific models when we talk about each particular model, and we'll calculate degrees of freedom for a bunch of different types of models as well.